introduce Wojciech, pronunciation Wojciech Hellwing. Wojciech has obtained Marie TV individual fellowship and will join us September, perhaps, or maybe a month later or a month earlier. And today it's a first occasion to introduce him and his research about non-standard cosmological tests of gravity. Very welcome.
Thank you very much for the introduction. First of all, it's a great pleasure finally, after so many months of excitation, to have a chance to present myself here. I mean, I learned a lot and informed myself a lot about this place. It's a quite long history and definitely looks very, very exciting for me to join the CFT crew in a couple of months. I was really excited. So finally I have a chance to meet you all in person and present myself. First of all, I would like to apologize before I start for a delay. It wasn't planned. Unfortunately, Polish Railways changed the timetables for the trains without notifying me. And of course, it doesn't mean I have to be notified. It's not like after 6 years in UK I attained some kind of arrogance. I'm not the British Queen, but nevertheless, I really apologize for being late and thanks for waiting for me. I have a lot to tell you about today, but I usually respect other people's time, so I definitely gonna skip a couple of slides since I have a broad scientific interest. My hope is that I will still get another chance in a couple of months to present the second half of my research topics, and basically thanks to this I will try to invite myself for another seminar. So presently I'm a research fellow at Institute of Cosmology and Gravitation, University of Portsmouth. This is a nice panorama of the harbor city. Portsmouth is a famous city because it is one of the oldest Royal Navy headquarters and naval base. And before the establishment of this university, which is actually very young, it was established in 1992, there were just sailors over there and local peasants, basically, or basically farmers. Now there's a really vivid city, constantly developing, and actually it has one of the strongest cosmological institutes in the whole UK, and maybe not so many others when it comes to sciences, but actually it's a very good place to study GR if you think that, well, I'm studying gravity and cosmological scales, because the name itself says that it's a Cosmology and Gravitation Institute. But as our director said, that I'm really, really excited to announce that in half a year all my presentation will start with this background and with this logo, which I will proudly show around as a member of Centrum for Theoretical Physics. I will be presenting some research at the very end, but I wasn't sure what kind of audience we have here, how much about modern cosmology you know. So I'm gonna, for the benefit of the doubt for all of you, and myself also, I will give you kind of a crash course introduction to the modern cosmology and the problems we're studying in the first 50 minutes, hopefully. I try to not to rush this too much, and then I will try to focus on some interesting new results I have developed in a couple of last years, maybe focusing at the very end on the newest results. And most of these results were obtained in the collaboration with many interesting scientists, most of them based in UK. But just for the curiosity and for the courtesy of their research and the collaboration, I will name them here. Ben Bos is Solmak Bos are two brilliant PhD students I had the privilege to work with. The surnames are just coincidental, they are not related to each other. Ben is based in Portsmouth and Solmak is based in Durham, which I spent my first postdoc. Bajuli is the researcher from Durham as well, and Kazuya Koyama is my let's say, line manager in Portsmouth, because this is the language we use. Maciej Bieliksik is my long-lasting collaborator. He's also obtained his PhD in Copernicus Center in Warsaw, like myself. And Carlos Frengadi Nazar, I'm a more serious scientist. I'm collaborating in everyday basis. So let me start again with the current model of cosmology, standard model of cosmological model, which is called lambda CDM, and basically name stands for itself. First part is cosmological constant, therefore lambda, Einstein cosmological constant, and the second part of the name is abbreviation of the cold dark matter, basically the pervading form of matter in the universe. It's a very successful model. It's an amazing model because with the only use of 6 free parameters can explain huge amount of observational evidence. But it's also a very ugly model. I'm not satisfied with it. It's a purely phenomenological model. Well, not purely. It has some solid ground physics, but it describes 95% of energy tensor content of our universe in a pure phenomenological way with nothing known a priori about Lagrangian of these two things. I mean, namely dark matter and cosmological constant. So what is the standard model? Because we don't have anything better at the moment. It doesn't mean that we shouldn't try to find anything better, but we don't have anything better. And we need to find new tests and possible problems with this model, because when stress testing the theory, you usually can find small cracks in it, and maybe these cracks, if you follow them, can lead to a new fundamental theory. So basically the standard model of cosmology is based on the hot relativistic Big Bang. Basically describes how the universe expanded and cooled down from the initial redshift of 10 billions, more or less. So this was roughly 40 billion years ago. And we can ask ourselves, this model includes all physics relevant to cosmological observations? Or might it be just the simplest approximation we can get away with the current level of evidence? Well, we don't have to decide, because it's a good science to operate under the assumption that this standard model of cosmology has all relevant physics, unless or until the observations forces us to improve the model. But it's also a good science to pay attention to apparent anomalies, consider tests that might help us determine which, if any, are real, and explore what the anomalies, if real, might teach us. So basically this is something I'm trying to do since the beginning of my PhD studies, try to look for the holes and cracks in the major beautiful facade of the standard model, and try to learn from this and try to see how far we can go from the standard model and what we can learn about this. So I would say the lambda CDM is doing great. This is the usual picture you can get from nearly all cosmological talks at present. Well, I wouldn't say that. Actually, I was a little bit tricky. I would say it's doing fine, because, as I said, it's really a phenomenological model. So this funny cartoon, the picture of the cosmology marches on, I think is not far away from being still true now. So we still have no plenty of the idea what is the physical meaning or physical nature of the most of the ingredients of the universe. Nevertheless, we still can explain a lot of observations under this general assumption of this model. So basically this model is based on two revolutionary ideas that were proposed around 1980. First is that the universe undergo cosmic inflation at a period, at a very early phase after the Big Bang. This cosmic inflation was the period in which universe expanded in a blink of an eye of many orders of magnitude, basically from the subatomic scales to the size of a peach of orange in the 10 to minus 34 seconds. And because of this mechanism is a hypothesis. This mechanism provides natural seed for structure formation. Basically, quantum fluctuations were stretched to the classical sizes and then imprinted over an energy tensor content of the universe. And this was the seed that later provide the structure we see today. And the other revolutionary idea, also that were really, I mean, it was coined before 1980, but it was really get its most evidence or start really be convincing in 1980, following Vera Rubin observations of rotation curves of galaxies, is the dark matter. That most of the matter in the universe is in the form of dark, non-baryonic or baryonic dark matter. Well, baryonic hypothesis of dark matter was falsified a couple of years ago, also thanks to the long-lasting heritage of Bogdan Paczynski and many tests he proposed. So we know that most of the dark matter is actually non-baryonic. So we have this privilege in astronomy that the light travels with finite speed, which means the farther we observe, the earlier we see the structures, and the earliest structures we can observe are encoded in the cosmic microwave background radiation, as uniform radiation afterglow of the Big Bang, which has tiny perturbations, fluctuations. They are really tiny. There's only 10 to minus 5 of average, this fluctuation. There's really homogeneous. If not, logarithmic scale, here you wouldn't see anything. And these tiny fluctuations are already, coming from the quantum fluctuation, from the inflation, are seeds for galaxy formation, and the structures we observe in the universe now. So basically we have this snapshot of the universe, how it was looking like. It was only 300,000 years old. It's very nice because this gives us initial conditions, and we can start to make a kind of a control environment experiments based on this, because we know how the universe was described back then. And actually we can still learn a lot, awfully a lot, from this simple picture from the early universe, because when the universe was young, the physics was simple. It's mostly linear regime, and you can describe this using linear theory of perturbations, and this is what you get when you try to describe statistical properties of these fluctuations of the temperature anisotropies in this CMB. The points here are basically actual measurements from the Planck satellites, the newest one you can get from 2015, with some error bars. Of course, low multiple means the larger part of the sky. Therefore, at the lowest multiples, we are constrained by cosmic variance because we only have one universe to observe. So at the larger scales, we don't have many realization of the density field. That's why the error bars are really huge here. But of course, at the high multiples, the error bars are tiny because we have thousands of realization of this particle scales fluctuations in the sky. And the green line is the best fit model, lambda CDM model to the data. So this is one of the best known cosmology predictions fitting the data. Nearly perfectly. Of course, some problems on the low multiples, but this is not significant due to cosmic variance.
How many fitting parameters?
Well, this is my next slide. So you can get away with only 6 free parameters because you have no information whatsoever about these parameters. You need to assume something, of course. Basically, I'll just say this is 6 parameters to describe my early universe, and I can just derive them by measuring this fluctuation. These 6 parameters are basically the total non-relativistic baryonic dark matter content, total non-relativistic matter content, including dark and bright, size of the acoustic horizon, sound speed horizon, basically sound speed and its horizon at the early universe, just before couple of thousand years before the CMB was emitted. Optical depth to the last scattering surface. Basically, this parameter tells us how quickly universe was reionized later. Once it's become neutral, then later new stars form UV radiation that reionize the universe, and basically this optical depth tells us how this process proceeds. This is the slope of the primordial power spectrum. Basically, if this would be equal to 1, we would have completely scale-free initial power spectrum, which is also known as Harrison-Zeldovich power spectrum. Just because it's slightly less than 1, it means that the large-scale perturbations are slightly more favored than the small-scale perturbation. But this is very tiny deviation from the pure scale-free. And finally, the last parameter is the normalization of the scalar perturbation amplitude. Basically, it tells you how much of the power from inflation you carried away before their combination. The larger this parameter, the more perturbation you would have in the CMB. And by the way, just the 6 parameters and the power spectrum I will show you before is already 40 sigma detection of non-baryonic dark matter at redshift 1000. Because the precise position of the concurrent acoustic peaks here, position of the first, second, and third peaks together gives you this strong inference that you cannot basically produce these peaks without big amount of the non-baryonic dark matter. So basically, we have this initial condition, we have this snapshot of the universe was young, and now we try to understand 14 billion years of cosmic evolution, because what we observe is actually late universe. We observe galaxies, which are the result of the many billions of years of gravity acting on this primordial perturbation and forming collapsed structures. And actually, we can also describe more or less the density field in the universe together with galaxies and the matter using very simple Fourier power spectrum of density perturbations. So we have constraints on the large scales. As I said, they really fit very, very well the lambda CDM predictions. We have some smaller intermediate scales constraints coming from the galaxy clustering, which is you can obtain from currently present huge and deep galaxy redshift space catalogs or surveys. Then you have a small scales. Small scales cosmology means intergalactic scales prediction. So black line is the CDM prediction, but you have some interesting alternatives like warm dark matter, for example, which will predict slightly different shape of this power spectrum. And this can be measured basically by counting number of dwarf satellites, but it's very hard to obtain prediction for this. And this is one of the parts of the research I'm trying to focus myself into really a lot recently, especially because it's one of the specialization of the Durham group, which I spent 4 years in. But unfortunately, I won't have enough time to cover this because it's a very deep and complicated topic. Basically, but you need to try to understand what kind of structures you can expect on the small scales, cosmological small scales. For this, you need to conduct very high resolution computer simulations of dark matter only, also including baryons, because I will show later baryons are very important at the small scales. This is just an illustration from one of the big projects I conducted over the couple of years. It's called Copernicus Complexia, which means Copernicus conundrum. This was a high-resolution simulation when you try to obtain the census of Milky Way-like structures in the local universe in the 2 competing dark matter models. We learned a lot from this simple simulations, and then later we try to extend our questions. We can learn a lot from these simple simulations, but unfortunately, as I said, I'm a little bit late. I don't want to take much of your time, so I will just show this in passing.
What was actually on that picture?
that was just rendering of the dark matter density field. Yeah, I'm going back, but this is the dark matter density field. The thing that the reason that you see the sphere is just because we need to make a sacrifices, because all computers have finite amount of RAM, and we'd like to have as much as possible volume elements. So we just put a sphere of very high resolution, surrounded by the low resolution in the simulation.
That is a density or
Density of the dark matter.
Dark matter where?
In the local universe. In the local universe, yes.
So what
Please,
go in the gap with Milky Way, as you said.
Oh, because Milky Way itself is a galaxy, and we can observe our local neighborhood with the
That could equally be in Andromeda.
yes. So this is statistical approach to this. I mean, of course,
Would that picture imply for a completely...
I would like you not to focus. I was just not, for this. You would have to wait, unfortunately, for my second seminar. No, I'm really sorry. I won't answer this because we start to going on a tangent that would take us away from my main topic. I would just want to show you in passing that this is the other focus of my research.
The reason why asking is this picture are beautiful unless you know what they are showing.
I fully agree with you, but as I said, please forgive me. I don't have time enough.
Well, then maybe you should show the picture which are relevant, because I had always a picture...
You would understand this is relevant if I would give you in.
We are totally
Yes, but I think both sides have made already their points.
Thank you. Thank you very much. Maybe that's a mistake. I just want to show in passing that I have a much broader scientific interest than just modified gravity or GR. If you want to learn more, please ask me after the seminar. I will stay here for late afternoon today. So going back to the main topic, which is standard tests or non-standard tests of gravity cosmological scales, we have some evidence from the accelerating universe, and I won't have time to go all the interesting evidence we have from observation, but I just show you the most compelling one. By the way, also the first one we got. It was Nobel Prize in 2011, given to Perlmutter and Rice and Schmidt. So they shared the Nobel Prize for discovering of the fainting of the faraway supernovae. So what I'm showing here is the luminosity distance diagram with the data points over here, basically, and the redshift corresponds also to the distance from this faraway supernovae to observer. The larger the redshift, the farther we see. And what they observe is they observe the following: that the very distant supernovae were so dim that even if the universe was completely empty, they couldn't be so dim. What I mean by dim? Because the more expansion was before us and the emission of the light, the dimmer of course the flux drops with the square of the distance. So even if the universe was completely empty, it couldn't expand so fast to make this supernovae at this high redshift so dim. So that was really, really compelling evidence that there must be something that pushed the universe faster than just the empty universe. Of course, the background in the cosmology is described by the Friedman equations and basically assuming GR. And this you can basically express in the contribution to the total energy density of the universe by different relativistic and non-relativistic components. And this is usually done as a relativistic component. This would be photons, total mass, non-relativistic mass, and some vacuum energy. And it shows out that basically the best fit with many sigma, I think 4 or 5 at least, for the supernovae diagram is the universe dominated by the vacuum energy, which would be accelerating, not slowing down. Why would you expect slowing down? Because if the universe would be filled with matter, attraction of the matter would slow down the initial impact of the Big Bang, and we should basically slow down the expansion. But actually what we observe, expansion is accelerating since at least 7 billion of years. That's very compelling evidence that the universe is accelerating. And where's the problem? Well, the problem is that how you interpret the equation you describe with the universe. So I quote on this instance Jim Peebles, a great Canadian astronomer who's basically spent all his career in the US, who said at the General Assembly of International Astronomical Union in the year 2000 the following words: "The elegant logic of general relativity theory and its precision tests recommend GR as the first choice for a working model for cosmology. But the Hubble length is 15 orders of magnitude larger than the length scale of the precision tests at the astronomical units and smaller, so we are really present with this spectacular extrapolation." So I have to bear in mind, whenever we describe the universe as total, use background solutions, we extrapolating GR of the 15 orders of magnitude, just because we need to assume that GR is valid to describe the background. Even though we have now more observational tests of GR coming from the gravitational waves or basically timing of the small pulse or of the pulsar binaries, all of this still comes from the regions of space and strong fields that are very, very small compared to the Hubble horizon. So bear in mind that we have this extrapolation. That's why if you even forget about the lambda problem, which I will describe in a moment, it's still really, you should be really careful when you use GR for the whole universe, and that's why we should try to come up with the new tests of this theory on larger scales than the, of course, solar system. So Einstein gravity can be described in a very simple way by using Einstein-Hilbert action.
Excuse me, this permuter observations challenge sometimes, right?
Yes, but this challenge was then a rebuttal. It wasn't based on valid. There was some logical mistake they made in the process. So they really stand clear, and it's very hard to really challenge them. Basically, if you separate the Einstein-Hilbert action, you have three major terms. You have Ricci scalar that corresponds to the curvature. You have Lagrangian that describes the total matter content, and you will have the lambda, which is the cosmological constant. So the problem with this picture is that in order to match the observations, this quantity needs to be fine-tuned by 50 orders of magnitude, because its natural value predicted by the quantum field theory is 50 times order of magnitude larger than the observed one. And it's very, very, very hard to reconcile why it would have to be so small. So that's why it gives rise to this idea that we could probably construct different theories, effective theory of gravity, that would set this value to 0, and we try to explain expansion of the universe by just modifying the Einstein gravity. And why you still need to be careful not invoking this lambda term as dark energy. Let me bring you an example from the very, very, I think, educative example from the 19th century, when Urbain Le Verrier, French mathematician, proposed the existence of Vulcan, a hypothetical planet that should explain the anomalous perihelion of the Mercury. So Le Verrier really studied, I think, 20 years of observation of the eclipses of the Mercury, also transits of the Mercury, and he have found out that basically the perihelion of the Mercury orbit is precessing, and this picture couldn't be completely explained at all within the Newtonian gravity it was known back then. The same Newtonian gravity described perfectly well orbits of Venus, Earth, and all the celestial bodies. So he postulated that there must be an additional planet. It's very close to the Sun, that's why we cannot observe it. It must be very small. This planet was called Vulcan, and by introducing this Vulcan, he could explain this anomalous perihelion of the Mercury orbit. And later, we of course have found out that Vulcan does not exist. What we actually had to do, we had to change our theory a little bit, because it couldn't describe properly the gravity in the presence of a very massive body like Sun. So actually, this proving Vulcan's existence is also very central to Einstein, because it showed that his radical and bizarre new picture of gravity was actually the right way to see the universe. Of course, Vulcan was never discovered. We had to change the theory. So this is very informative to learn that maybe before you invoke mysterious dark energy or mysterious repulsive fluid, maybe you can basically still explain the universe by a little bit adjusting the theory or trying to find new one. The problem is, and this is all this collective line of thought become motivation for one of the main goals of the precision cosmology of 25th century, and we have this multi-billion of dollars, or million of dollars grand challenge and scale observational campaign like SDSS, Standard Sky Survey, Euclid Satellite, Dark Energy Survey, or Dark Energy Spectroscopic Instrument, in which I'm involved at Portsmouth, and all of them are targeting to really map the universe at larger scales, provide us spectra of hundreds of millions of galaxies to test the GR on intermediate cosmological scales. The problem is that there's many different ways you can modify it, and of course, to test the GR, you need to also know what kind of alternative you can expect, because we still are working on a logical assumption level. So, how you can basically realize modification to gravity? One main different way. All of them need to have GR curvature terms, so this is Einstein-Hilbert action that can describe the universe. All of them, of course, need to contain matter, but then you have completely different stuff that can accelerate. In standard model, you have lambda. You can have weakly coupled scalar field that will be rolling down to some completely unknown arbitrary potential, and this would produce accelerated expansion. These models were called quintessence models. You can have a scalar field that couples to the higher derivatives to the canonical terms. This would give you complicated models that come, I think they're called kinematic gravity braining. You can have something, it's called f of r. Basically, when you generalize the Ricci scalar to the functional of its own, it's nonlinear function, but basically it's one of the most popular version of the modified gravity. It has very interesting features I will tell you about in a moment. Or you can have something that really depends on also the higher kinematic couplings to the to the scalar field also has own potential. And all of these models in particular are free of ghosts and can describe lambda CDM universe at the first order approximation. The problem begins if you really consider what different avenues you can go to search for the ultimate new fundamental theory. So modified gravity is not a simple term. It's just term in which we put many different possible ways to modify this gravity. This is a slide I borrowed from Tessa Baker, nice presentation. And it's impossible just to sit down and try to work it out from the first principle, all of these models separately, and see what kind of observables you can arrive. Basically, you would need to have hundreds of PhD students, very talented, and maybe thousands of students, hundreds of postdocs, and basically need the infinite amount of computational time and maybe resources to do this. So actually, another scenario is to try to focus of the main two classes that share some similarities on a physical level and try to see where you can go from there. And actually it's possible because all modification to gravity needs to be protected in the vicinity of the massive bodies like solar system. Why? Because we have a very stringent test of gravity in the solar system, also around massive bodies like pulsar binaries. So all of this modification to gravity, which by the way, all of them actually predicts extra degrees of freedom, because of this extra degree of freedom, they would have a spatially fluctuating scalar field, of course, and this would produce gradient. Gradient produces fifth force, and they would, of course, break the equivalence principle, or you observe this extra gravitational force in the solar system. So they need to protect this somehow. How they do it? They implement so-called screening mechanism, which recovers GR on small scales or in high curvature, high density regions. And there are basically two main different way you can do it, and okay, there's nearly no possibility. All of this modification you can basically narrow down to these two different ways of screening gravity, this extra fifth force at small scales. First is the chameleon mechanism, in which the screening depends on the local density, local curvature. Basically, the higher the curvature is, the weakly the coupling is of the fifth force to the matter, and basically you make the scalar field very heavy, and it cannot change the dynamics on small scales. And the other is so-called Weinstein.
Fifth force, whatever it is.
It's the gradient of the scalar field. Fluctuating part of the scalar field has gradient. When we have a gradient,
I don't know what that scalar field is, or it's whatever. Why don't we see it in the earthly experiment?
but this is what I'm saying, because all of this modification to gravity invoke the screening mechanism. And you have two families. One is chameleon, is environmentally
That
dependent.
scalar field somehow is what? What should be the property of that scalar field that I don't see in the experiments on my cup of tea?
I'm trying to explain, if you would let me finish.
I'm listening, but
So there are two screening mechanisms. One, as I said, makes the scalar field, for example, very heavy around the massive bodies. If the scalar field is heavy, the fifth force propagates as Yukawa coupling and will be very, very small. Will be so small that you wouldn't even find it in the Earth-based measurement. And the other mechanism make the higher derivative of the scalar field, screen the scalar field itself down. Again, would make the scalar field decouple from matter, and in the presence of the massive bodies, you wouldn't feel the fifth force. And this is very rich phenomenology, of course, and I wouldn't like to spend too much time on the details. What is important, they have very different properties. This depends on the mass and...
Basically, you somehow smuggle into the theory additional length scale, right? The Planck mass defines the only length scale which is present in the gravity, and now that says that it has a uniform kind of interaction across all the scales, right?
Yes.
And except maybe for very short distances. And now you have to smuggle into a different length scale, because otherwise the mechanism couldn't work. Right?
Yes.
If there is a one length scale, there is a one length scale. If you need another one,
Yes.
you have to introduce it somehow, right?
So basically all these theories also postulate violation of the universality of the coupling constant. The scalar field would not couple the same at different scales. It will couple differently to the matter field in the vacuum approximation, and the coupling constant will vanish in the presence of the massive bodies, basically will making the fifth force not affecting dynamics on the small scales. So basically the difference is that this depends on the local curvature, basically local density, if you like. Around the dense bodies, the fifth force will be screened out, so inside solar system, inside galaxies, and this depends just of the distance from the massive body, because this mechanism, Weinstein mechanism, depends on the mass enclosed. They have different properties because of that, and there's two phenomenology you can try to test.
That raises, I mean, this is a try to solve a problem by introducing another one. Because there is always...
I'm not saying that.
Why this additional length scale just looks like that? You might have a modified gravity, a gravity which is protected in the length scale of
I
the
agree.
solar system, but why not on the length scale of a galaxy? Or why not on the length scale of a cluster of galaxies?
Okay, I fully agree with you. It's another fine-tuned problem. I'm not the advocate of modified gravity theories. What I tried to do was try to find...
Why don't we see the elements or a taste of the fifth force in the heavy ion collisions, where the energy density in the central repeated region is essentially as close as possible. We can experimentally test the initial state of the universe.
No, because all these models have this...
When is this fifth force born, so to say?
This fifth force will manifest itself...
With the Big Bang?
No, only on very late times, and because when the density drops.
What happens if all over a sudden the universe has been created by the Big Bang, and then there is another phenomenon when something is being created from somewhere? So how come that this fifth force came into existence?
No, the fifth force came to existence when you have developed the scalar field long enough. The problem is...
Yeah, but that is not the answer. So how that scalar field developed? I mean, you said that at the very beginning, but the Big Bang, there is no fifth force.
No, I didn't say there's not fifth force.
You hide under that name.
I said that because of the high density of the early universe, all the fifth force is screened out. All the universe is screened out, so you don't see any manifestation. This fifth force does not couple to matter at early universe because the universe is too dense. Once the density drops down, you can start to develop higher irregularities.
If the effect of the fifth force increases with the lowering of the density, why don't I see it in my cup of tea?
Because it's still a huge...
It's much lower density than that was.
No, you see it because you see no phenomena which are...
No, I'm sorry.
Screened by this mechanism which
I'm not
protects
taking it.
Your cup of tea is still orders of magnitude, it's 27 orders of magnitude larger than the average density of the universe. So that's the reason. You need to be close to the average density of the universe, which is 10 to minus 27 grams per cubic meter for the moment. So please...
A good experiment with almost perfect vacuum. That should be done in it.
No, because it's still it works on the large scales. You cannot separate it from itself, right? No. The problem is, if you would follow me, the scalar field is to fluctuate.
A simple way of saying that it does not exist.
No, please. If I could continue, I mean.
That would be the simple. If it does not exist there, and we cannot prove it in the heavy ion collisions, which are the only experiment now we have, which can approximately see what happens in the initial state of creation.
No, this is effective field theory.
Vacuum, so it happens somehow in between. So it's conveniently chosen a quantity to fit the data.
Of course, I never said no. I'm not. So please listen.
That is not what the modern science should do, because that is a clear violation of a proper way we are thinking about the science.
We are going on the tangent again, but if you please finish me, allow me finish, I will try to go to conclusion.
For listeners,
I agree.
Not for the speakers.
I agree.
The fact that I'm going on a tangent, or whatever you will call it, is irrelevant. Because I try to understand something.
But really going to Popperian philosophy.
No, because I mean the answer
by the way,
is here. The
let me
answer was
explain it
scientifically
in this way. Many people
not
of the
honest.
audience.
That's what I'm saying, that the answer to the question that this is just the fitting of a parameter, and I mean this is not the scientific answer.
Let me maybe try to rephrase it in a little bit more general way, a little bit less general way, but maybe more understandable for the speaker why we see a problem. You know, many people around have been involved in some moment of their life in theoretical interpretation of, for example, very precise measurements of energy levels, difference of energy levels, and so on and so on. And you know, we think that way: large distances, small energies, small difference in energy levels, very high precision. It all has to come together. There is no way you can have a force which acts only on large distances and is not visible in
There is a way.
very precise atomic experiment.
Excuse me, there is a way. If you break strong equivalence principle, who said you have to have strong equivalence principle?
Okay.
Because I'm saying most of these theories predict that the coupling constant is not universal, and you might not necessarily couple to baryons with the same strength as you couple to dark matter. I'm not saying I want to basically create completely philosophy. My approach here is that there's many phenomenological theories on the market. I'm trying to find this from the skeptical point of view. I try to find observables that would tell us that these theories are also falsified by cosmological observations. Okay. Because they really put a lot behind huge machinery to hide this from the local universe constrained solar system. I'm not satisfied with this. I'm trying to find a smoking gun of these old theories that would say, look, it's either GR or you basically, all your theories cannot match the observations in cosmology. I'm not focusing on this high strong field limit or small scale limit, of which I'm not a specialist. Although I assure you that development of these theories took this into account and they've been scrutinized against the strong field limit and also baryonic experiments on in our planet. Of course, they have this not very appealing aesthetically mechanism to hide these modifications, but of course they cannot get away forever, because otherwise there would be just multiplication of the same theory. You cannot predict that you have a really good theory if you just introduce another functional and you don't predict anything new. So what I'm trying to say, I try to find a way to falsify these theories from the cosmological point of view, because for me they are not the same, less appealing than the standard model. It's no matter if it's modified gravity or dark energy, they're still fine-tuned. So I try to find at least this test that would tell us that, look, stop wasting time of the bright young student with this modified gravity theories, because they are not, they cannot really explain the.
At that point, you have our full support. Continue.
Thank you very much. Maybe I should rephrase myself differently. So people came up with different scales and different observations that you can probably try to see if the GR is still holding, because basically ultimate to test would be if there's this theory that say it's not GR, will predict something else than GR. If we observe this, that's something that GR could not explain, this will be a smoking gun. On the other side, if all these GR tests would be converging on GR, there would be no motivation for exploring this modified gravity whatsoever, because they will just be basic epicycles. So you can observe galaxy strong lensing. This is very small scales. Stellar dynamics inside galaxies, also sub-megaparsec scales. You can observe the dynamics of the galaxy satellite. This is up to megaparsec scale. Then there's weak lensing of galaxies. And finally, going to larger scales, you can observe clustering of galaxies in redshift space. So all of this will probe the gravity on different scales, and most of these models, modified gravity, will predict some kind of deviations, because as I said, if you go to large scales, you go to low densities, this fancy mechanism cannot work for the whole universe, otherwise they would be just equivalent to GR. So you have this specific narrow, it's not so narrow actually, specific window where you can expect this modified dynamics, this fifth force should affect galaxies and should affect observables. And if we can construct robust tests of this, we can falsify this whole class of theories. So I'm actually on the side of being really scrutinized and being really conservative, because I'm not also pleased with invoking random theories instead of random perfect fluids. So let's assume how we can study growth of cosmic structure. So basically we have inflation, Big Bang, then we have this snapshot of the CMB, so we know how the universe was statistically described by the density field of the universe was described when the universe was really young. And then after 40 millions of evolution, we can observe the very much clustered galaxy density field. So basically you have to realize that this initial primordial density fluctuation were order of 10 to minus 5, and after 40 billions of years of evolution, it can grow up to 2 million of density contrast. So basically this is 11 orders of magnitude in density contrast. No linear theory can, of course, describe such a process, so you need to resolve to non-linear methods, and the only method we have now is basically computer simulations. So of course they are still approximate, but the only way they can really probe the regime of structure formation is to basically teach the computer the all laws of physics you know, all the assumptions you put there, then you run the simulation, and if something goes wrong, you may challenge your assumption you put in the process itself. So basically, of course, I would really like to have in cosmology equivalent to the control environment experiment that, for example, particle physicists have on Earth in CERN. But of course, in cosmology, we don't have anything like that. We observe one universe, we are inside it. So the next best thing we can do is to construct the theoretical models of the universe, evolve them, and see if what we get is really something reasonable. For this, we use supercomputers and some trained personnel to run them, and we use them cosmological computer simulation to try to extract nonlinear regime of galaxy formation. And if you start putting these models into the computer simulation and try to focus only on deviation from GR, which I will start to do from now on, you can realize that quickly there's some interesting deviation from GR immediately on the scales that should be manifested by the observation in the galactic surveys. So for example, most of these models, it doesn't matter which kind of, these are two different screening mechanisms, will predict much higher variance of the, much higher clustering of the matter at small scales. This is just a Fourier mode. So inverse of this is 6 megaparsec, this is 6 megaparsec, this is 60 megaparsec. So this is enhancement of even 40% with respect to GR. The problem is you don't observe the...
Just ask a question because it's something which is quite personal. I mean, about 20 years ago, I led a summer school in cosmology together with Manfred Linder. Maybe you have heard about him.
Yes.
Now a director of Max Planck Institute in Heidelberg. And the school was, Professor Kozinski was a student at that school, and we just considered exactly the same question. And I was very ready to contest the fact that you can evolve these fluctuations basically by 11 or whatever orders of magnitude, still without reliable nonlinear method. But Manfred said, well, you know, it's just linear gravity works perfectly. That's
okay. So I will say,
has something changed?
so what is done in these simulations to pretend what the simulations were? Okay, there's a problem between bilinear.
You mean Newtonian gravity?
Newtonian gravity basically.
The only GR part here in the simulation are the expanding background.
No.
They are not linear gravity. Gravity is nonlinear, but intrinsically nonlinear.
No, but somehow linearized. I remember from that time the simulations of the
Oh, so we don't have it linearized anymore. We have complicated algorithms that go fully to non. I mean, there's still
But she was then very successful, at least I was
But
told.
only at larger
Scale, yes.
where this density contrast is
It's still small.
one. If you approach one,
yeah. If
sorry, you have
So now you just consider much smaller scales and then this
no, that's a very good point because 20 years ago we didn't have enough computer power to do this.
intuition 20 years ago, yeah.
Yes. So also, if you just express this in the configuration space, not Fourier space, you still see that there should be much more perturbation of matter on small scales in modified gravity than in GR. The problem is you don't observe, and not on this in the direct way, perturbation of matter. What you observe usually is the luminous tracers of the underlying density field, which are galaxies. And the galaxy formation is complicated. First of all, you need to realize that these tracers are biased, because in order for a galaxy to form, it needs basically the clump of density it forms, it needs to detach itself from the universe expansion. For this to happen, it has to cross some kind of a threshold barrier. It has to be big enough density to switch itself out from the expanding background. So basically the galaxies only form on top of the peaks over peaks. So this is a biased picture. And basically efficiency at which these galaxies form depends in general on the local density and also on different complicated microphysics of gas. So this is complicated. You cannot use simple physics to really trace it. And let me just illustrate this in a very nice, of course, propaganda picture, but this is a slice from our hydrodynamical simulation. So not only dark matter, but we also try to involve all complicated microphysics of the interstellar gas, including star formation of the supermassive black holes, simplified way, of course, which produce asymptotic galactic nuclei feedback, supernovae explosions. So once you involve all this complicated baryonic physics, you will see that the universe, this is dark matter part of the simulation. We have plenty of dots and clamps, but only very few of them. This is the stellar light we have in fake galaxies we produce in simulation. Will really be hosting a galaxy. So that's why galaxies are really biased tracers of the underlying density. Of course, that makes it much harder to map the prediction of the theory of the observations. It's even worse in the case of modified gravity theories, because some people run this hydrodynamical simulation of galaxy formation in case it's a kind of a simplified scenario when you have this modified gravity. Is it good or not theory? You just want to see what happens. This is kind of a really Gedanken experiment, if you think, kind of a final Einstein way. In the worst case scenario, the two effects are completely degenerate. Basically, the more feedback you have from this energetic baryonic effects like supermassive black formation of supernova explosion, you can have more clustering with respect to dark matter. So basically the solid lines shows you the prediction of the modified gravity without baryonic physics, and the dot lines are predictions of the enhancement of the clustering with respect to GR of the same simulation when you start introducing this complicated baryonic physics. So basically they go in the opposite direction. So in the worst case scenario, you could hide all this modification to gravity because of the very effective baryonic physics. Unfortunately, you don't know much about baryonic physics a priori. You just try to measure this in the universe and model this in a reverse way. So this is a huge drawback. You probably can use this clustering for testing this modified gravity theories. And that's why, basically, in my opinion, it renders completely useless for testing modified gravity. One of the most popular probe, which is the weak lensing. As you know, from GR we know that the light rays of the distance photon basically follows the curved trajectory because of the light space-time be curved around massive bodies, and this can produce statistical deviation of the faraway galaxies pictures. We can basically, they are a little bit twisted around, and if you measure thousands of these galaxies, even this very weak effect, you can measure amount of shear and convergence, how much this picture is being totally disrupted. The problem is the amount of this deflection depends on the total projected matter between the observer and the source. And as I showed you before in a second, this total matter spectrum behaves differently than just dark matter. You need to know a priori effectiveness of the baryonic effects to be able to measure this. So this weak lensing isn't a good is not very good probe to try to test GR on cosmological scales, because you can hide non-GR signature in the baryonic effects. So this is not good. I'm trying to focus a little bit more. So therefore, I tried to look for something else a couple of years ago, actually following a footstep of my late supervisor, Roman Juszkiewicz, and I looked at the galaxy velocity field. Why is that? Because in the linear theory, velocity field is proportional to the density contrast, so this is basically reflecting the continuity equation. So in integral flow, the velocity in linear theory is proportional to the gravitational acceleration, and because the velocity is kind of two integrals away from density field. First you integrate over the density field perturbation, and then you integrate over the time. If you have a tiny discrepancy in the dynamics, it will be integrated over the whole cosmic history, which makes even small deviation from GR will be many, many times amplified in the velocity field of galaxies, because you have 40 billions of years. Let's say if the fifth force only worked for 1 billion of years, it's already enough to emphasize and change the galaxy dynamics a lot. And I go back to the simulations and look immediately and find something drastic. So basically, if you remember the previous plot, the enhancement of modified gravity of the density field was up most to 40%. For velocity field, it can be as large as 100%, and it also stretched to much larger scales. This is basically plotting again, I'm always taking ratio with respect to the GR. So deviation from GR prediction, the galaxy velocity field at different epochs of the universe. So at the present, it should be huge deviation of the galaxy velocity field with respect to the GR. This is in principle very good observable, but as I told you before, galaxy formation is complicated. So what about these baryonic effects? So we went back to the Eagle simulation project. This is currently state-of-the-art, one of the best we have at the market. Computer simulation that involves both dark matter and the galaxy formation, basically follows the evolution of the interstellar and intergalactic gas, and even forms something that looks reasonably well as good galaxies. And we know this is a good simulation because if you would increase the baryonic effects, you basically destroy all the observables. You couldn't much.
Saying that the simulation involves dark matter, certain model of the.
Of course, it involves cold dark matter. I'm trying to do one thing at a time, so we assume here lambda CDM, and we only play with GR, not we play with dark matter.
There is a universally accepted model of dark matter.
Yes, which is the cold dark matter. And we have found the following. When you go back to density field, this is again deviation.
That is the scalar field, right?
No, dark matter has nothing to do with the scalar field. This is some kind of elementary particle, weakly interacting elementary particle that was created and the universe was very, very hot. So this is what I plot here is the deviation of the power spectrum with respect to dark matter only. So basically this gauges the amount of these baryonic effects. So when it comes to density field, it can be as large as 10% on many order of magnitudes. But when it comes to the velocity, it can be at most of order of few percent, which is much smaller than this effect of modified gravity. So far so good. We are protected. We don't need to, if we want to follow galaxy velocity field, we don't need to we don't need to concern ourselves with the galaxy formation that much, because the effect on velocities is much smaller than the effect of densities. Let me skip this because this is something I don't want to cover at the moment. This is covering velocity, galaxy redshift dispersions, but I found something more interesting. So I'll go back to how you can use this in measurement. So basically, there are certain ways you can really measure the peculiar velocity of galaxies, because you have the information of if you have other source of information of how far away the galaxy is, and you can measure this by following some scaling relations. So, for example, spiral galaxies, the way the dispersion of the velocity of the spiral galaxies correspond to their absolute magnitude. So you have more or less something like standard candles for galaxies. So you can basically extract the information of the galaxy, how far away it is. Once you have this information, you can learn of the radial component of the velocity of the given galaxies. And one of the possible way to quantify this is so-called pairwise velocity correlation. And this basically corresponds, you have an observer here, you have two galaxies, you have only U1 and U2, so radial components of these velocities, and you make a pairwise average over many pair of galaxies. This actually estimator is very interesting because both pairwise velocities, because it's a relative velocity difference, don't care about the scales much larger than the separation of galaxies. They will only depend on the scales, on how much power and how much gravity is on the scale smaller than the separation of galaxies. And because, as I show you, the modified gravity, most of them predict some deviation on the intermediate scales, this will be very, very sensitive. And indeed, it is very sensitive. We have called it smoking gun, and we have published this letter in Physical Review Letters a couple of years ago, showing that even if you include some galaxy modeling, and we will try to be really, really conservative, you should be able to distinguish some modified gravity theories from GR with even 4 or 5 sigma significance at this separation. 4 or 5, bear in mind, is very, very large for cosmologists. It's nothing for particle physicists, I know, but for cosmologists, everything above 3 sigma is really significant. So we jump, well, we find something interesting. We should just go to the data and see if it's GR or not. So we did that. Let me skip about this for a moment. This is other way. You can also measure these velocities by using velocity correlation, not pairwise, but just basically taking the correlation about all the pairs in the sample, and the signal is also there. I just want to skip this because what we did. So okay, we took the data. Back then, the state-of-the-art catalog for galaxy velocities was so Cosmic Flows 2 catalog. It was made by Brent Tully and Hélène Courtois, with more than 8,000 peculiar velocities of galaxies within 200 megaparsec around the Milky Way. This is a nice presentation of the real data. This is our position of the galaxies. This is kind of the velocity flow of the galaxies recovered from the measurements. And I made this measurement. So basically, black line is a prediction of the GR. Red line is the prediction of one of the modified gravity models. That's a very strong one. And the blue points are the data. Wow, I jumped. I couldn't sleep overnight when I saw this picture. But you see there's something really wrong about this picture. You cannot see error bars. So when I did some proper error analysis, I obtained this. What a disappointment, as usual if you work with experimental sciences. So, but I was surprised why the scatter is so large, because at 50 megaparsec separation you should get much smaller error bars. Cosmic variance shouldn't be a problem here. Even at smaller separation you have hundreds of galaxy pairs. So I was really confused why I get such a big scatter. And then we start really looking into the problem on higher level of details. So Adi Nazir, my collaborator from Haifa in Israel, suggested that maybe because the velocity data only consists local universe, maybe actually the position of the local structures like Virgo cluster, Shapley concentration, basically our neighborhood somehow affects this observable, because velocities of course fills the large scales, but some of the velocity of galaxies will also fill the local nearby structure. As you might have heard a couple of years ago, there was a big buzz about great attractor discovered in the late 80s. So basically a huge structure towards Milky Way with all its galaxies falling. So we make this, we try to look into the simulation in something that really resembles local Milky Way like observer. So we put observer on a halo that has velocity similar to the CMB velocity, so basically velocity of the local group with respect to the cosmic microwave background. We put the observer on the galaxy that has the same mass as Milky Way. You recognize that the local neighborhood is very similar, so basically density contrast around the Milky Way local group is basically something like that, which we know from observations. And finally, we also asked there will be something like Virgo cluster nearby. And we immediately found out that actually really the environment matters, because we have so few velocities and it only covers our nearest neighborhood. Actually, we're breaking somehow Copernican principle because we don't have enough statistics. So this is, the black line is the prediction for completely random Copernican observer in simulation, and the blue and green line with the red shaded region showing you the variance is the estimator you would get if you include some kind of a local group, local structure modeling. So actually there's a huge striking difference, and also you can see the local group observer has a huge variance. It turned out the local structures like a Virgo cluster or these big massive clusters, they have such a strong gravity that they really affect velocity field of galaxies to the nearby 100 megaparsecs. So you cannot get away with just a simple assumption. I take the isotropic Copernicus homogeneous universe and try to compare what I measure with the predictions. You need to really model these complicated local structures to try to see what is the predicted signal from theory. And the same goes for the velocity correlations. So this was pairwise velocity estimator, so basically how much galaxies approach each other more or less, and the other one was just total velocity correlation. It's even stronger effect here. So this leaves us with a little bit bitter taste, because this is still work in progress. Even though we can predict there's a smoking gun in galaxy velocities, we should be able to see any difference, any modification to gravity there. So if we can make the measurement, we can confirm probably GR with 5 or 4 sigma on the intermediate scales. This would be a killer for most of these modified gravity theories, because they predict there should be some deviation from GR on these scales. Unfortunately, to extract this signal, a huge amount of the theoretical work is needed, but this is a work in progress. This is one of the things I put in the proposal for Marie Curie. I'm really looking forward to doing the following years, also including baryonic physics. And in the last couple of minutes before I finish, I just want to advertise there are different possibilities to try to test this modified gravity, not with velocities maybe. One of this is, for example, cosmologists really like to use something is called two-point correlation function. Basically, this express the excess probability of finding two galaxies at separation r. But the problem is, of course, you cannot measure this directly. What you measure is this from galaxy clustering. As I said, galaxies are biased tracer. You don't know how galaxies form. But we have constructed something we call relative clustering ratio. When we take the correlation function of one galaxy sample and divide it by the correlation function of different galaxy sample of different density. We take, for example, very massive galaxies, and then we take very light galaxies, so very sparse galaxy sample and very abundant galaxy sample, and take the ratio. It turned out that even though we don't know how the galaxies form and the bias mechanism can be different, the ratio takes away more or less this effect, and you can really see that measuring this in observations should give you strong signal at small scales of the modified gravity. At least you should tell you that some of the theories cannot really match the observations. Unfortunately, to be able to really take this prediction to observation, we need to we need to make the very large computer simulations, and computer simulations for modified gravity are very very expensive. They're usually 10 to 20 or even 40 times slower than this computer simulation of GR. A couple of months ago, we make some breakthrough with collaborators. We find a kind of a trick we can use without loss of the generality and the resolution. We can speed up the simulations. And as I spoke, we are running now the big simulation in the ICM in Warsaw that will be used in a couple of months to try to use this new clustering ratio to try to put this theory at test. And last but not least, going back to my really early times of my PhD thesis, when I was following Roman Juszkiewicz, and those of you who maybe heard of him, he was really a found guy of perturbation theory. And one of the things you could study back then was in weak nonlinear regime was some called clustering amplitudes. Basically, you take the central moments of the density field. Basically, if this would be purely Gaussian field, all the odd moments would disappear, and even moments would be just multiplication of the variance. But because gravity produced non-Gaussianity, these moments will grow, and because if you modify gravity, they will grow in different way in modified gravity theories, and you can take the ratio of these moments to respect to variance. This ratio are really flat and nearly scale independent, and you can go back to observations and see what happens. It turns out that's a huge signal for galaxy. So I take this kurtosis and skewness, skewness and kurtosis, and I model galaxies in a different way, and I have two different modified gravity models. It seems that this ratio at high, for very sparse galaxies are very noisy, but for some low mass galaxies, they can have few sigma detection threshold. Again, we need this simulation to finish to go back to observation and try to find this prediction. So basically, I try to attack the problem on different angles, not only velocities, also try to find observables that wouldn't depend on the total matter power spectrum. Because as I said, I'm not really satisfied with the current state of the affairs. I'm not satisfied by invoking this huge amount of new extra physics without really solid evidence that we need them. But of course, as I said, we need to explore all possibilities and see how far we can get away with. And of course, testing GR, I think, is one of the important things to do, because it's still extrapolation over 15 orders of magnitude. Again, sorry for being late. Again, sorry for being really vague about some things. But of course, this is a very highly complicated topic, and I didn't want to leave you unsatisfied with my answers. But of course, I'm happy to explain a lot more. You would have any more questions. Let me leave you with the final quote, which I follow completely, well, which I disagree completely. Alfonso X de Lerm, who used to be king of Castilla and Leon in 12th century, is acclaimed to say that he said, "If the Lord Almighty would have consulted me before embarking upon all creation, I would have recommended something simpler." I'm not agreeing, because if the universe would be much simpler, there would be no place for us to stay and wonder. And thank you very much for your attention.
constant is simple. Why we are not happy with it?
Well, I'm not happy with it. Definitely all this modified gravity theory, I think they're a little bit cheating in most of the introductory paper, because they still need some kind of a mechanism that would set true lambda to 0, right? Because lambda is just a universal constant of integration of Einstein equation. I think the problem arises when you really want to marry two things, which is quantum theory that would naturally predict the quantum fluctuation, because this is the most natural explanation of Einstein constant is the quantum fluctuations. And people are unsatisfied with this huge discrepancy between prediction and observations. But in the end of the day, I would say, well, Newton constant is also extremely small, and its natural value, if you would try to go to the grand unification scale, would be much higher. So maybe we are just unlucky, and because of some missing part of the puzzles, we have this Einstein constant to be very, very small. But as I said, it's still good to test GR, even though you might be satisfied with lambda, because you still extrapolate the whole theory of much larger scales than it was ever tested. But in order to produce some tests, you need to have something to test against, because otherwise you will have circular problem. That's why these modified theories at least give us a good rival to fight with, so to compare with. I'm happy with lambda as well. I mean, one of the goals I put on myself a couple of years ago is try to basically narrow this field, saying, look, you should stop working on these theories because they have no good motivation and they probably cannot even explain the data. It's very hard to do this, especially that it's become very, very large field and many careers were built on this. I'm still trying, and I hope to put some final remarks in 2 years' time after concluding my Marie Curie here.
I want to ask, in your simulations, the ones which you run with your group and also I think, do you use baryonic matter also or only dark matter?
With the modified gravity, we don't use baryonic matter yet. We want to, well, this is one of the things I want to develop into during my fellowship. But I run different simulations when I focus on the testing different dark matter models, which I didn't have time to discuss. And they are including fully the baryonic evolution, including AGNs, including supernovae, yes, all the state of the art. So definitely we'll have some meeting points to discuss for future.
Okay, I have two probably related questions. One of them is, how do these modifications of GR really look like when you look at the guts of the simulations? Is it the modification of 1 over R law, or is it introducing another field?
No, it's mostly, I mean, this is a very good question, because first of all, even in normal cosmology, we really treat GR very lightly. It's not really GR. The only GR part you have in cosmological simulation is the background evolution. Of course, some groups show that there's some small effects can be expected if you include all these degrees of freedom. And of course, no one really did that for modified gravity. So again, it's a little bit of cheating. It's effective field theory. So all this modification follow as a scalar field that is coupled to matter, and therefore you take the gradient to get the fifth force locally. And of course, you follow the screening mechanism because they also depend. So you're solving nonlinear equations, nonlinear Poisson equation, because you generalize a Poisson equation to be nonlinear, much more nonlinear. That's why they're more expensive, because normal Poisson equation you can solve by green function or Fourier grid. Here you cannot use this, but still, it's still phonological approximation. So there might be some, this is a very good point, because I know no one really looked into coarse-graining problems of this modified gravity. They can be even more severe than the coarse-graining problems in GR. So this is a very valid question, worry.
My second question is, they tend to be so much more expensive in simulation. So if you have to run through the nonlinear Poisson equation, that probably accounts for it.
Plus the superposition rule does not apply here, unfortunately. At least for the fifth force part, because it's not universal, it depends on the local density. That's why it makes it much more expensive.
A few months ago, there was some addition in media and information concerning the fact that this acceleration of the expansion of the universe is not really true. That there are experiments indicating. Well, if that was the case, then all this analysis would be supported.
But it's not the case. The problem is that how current media works, of course. There was definitely a paper trying to challenge one of the observations, but the thing is, the current model is not based on one observation only. It's the whole, it's like house of cards. If you try to take away one thing, it will collapse completely. So we have different evidences based on different physical mechanisms. So for example, I would say integrated
That doesn't look from your presentation that your house of cards holds very strong.
I would, well, GR house of cards holds quite strongly. I would say this modified gravity might not, again. But we have different observations. For example, integrated Sack-Wills effect. For example, if you have a big galaxy clusters, in this, if its gravitational potential will evolve with the expanding universe. If the universe expands faster than we predict, it will shallow the gravitational potential of this huge cluster. And now we have a photon that falls in, it gains energy, but because the potential change over time, it actually loses less energy than it gained because it's flattened out. It's a very strong effect, it's been measured, and it has no other theory to predict, to explain this except accelerated expansion. And plus we have other things, like for example, abundance of primordial elements up to lithium. That gives you the strong constraint on the total baryonic matter, and then you see that the total total content of the energy density is equal to critical density. There's no way to add up if there would be no dark energy. So basically there's many different observations that points to this accelerated expansion. And of course I would be happy because I also can be skeptical. There were some models try to explain this, but all of them did not survive scrutiny of the experiment tests we have. So with every new year we gain more and more insights into this different, using not only supernovae, we also now observe quasars, for which Bożena also worked a little bit. We also observe nearby universe in which we can see some evolution of the expansion, and all of this points to the accelerated expansion.
I have another question. You said that there is a universally accepted model of the dark matter.
There is.
So what are the properties? That means I have a universal accepted model. That means that I can write a Lagrangian for it or Hamiltonian or something, and then I can calculate the property of the dark matter without decoupling to the gravitation.
Would be great.
Would that be this?
It's universally accepted, but because we haven't captured the particle yet, it's based on the WIMP, weakly interacting massive particle, that would come from supersymmetry, for example. That would be the lightest supersymmetric partner, neutralino.
So there is no accepted model.
No, it's commonly accepted, but it's
If it's a supersymmetric, then
it's phenomenology.
It is accepted, just let me, because for the sake of gravity and galaxy formation, it just has to be a kind of weakly interacting particle with velocity distribution characteristic of a cold
but
gas.
then I'm asking what are the properties of this second
And that is irrelevant for the galaxy formation, and we are here at that part.
I didn't ask whether this model is right. I'm just asking that if this is a physics, and if there is a model of these particles, then
it's Majorana.
What does it mean generally accepted?
That is fantastic, and I'm completely flattened by the great achievements in this field, but I would like to ask a simple question. If there is this matter, what are the properties of that matter if it will not be coupled to the gravity, for example? I mean, if I have a cup of tea, which I have drunk, unfortunately, and it's coupled to the gravity field, and I can study the interaction between tea and the gravity, but I also, if I'm stupid enough as I am, I can also study the tea by itself.
Yes.
It's not, there are people who are making money on studying the tea by itself.
Sure, but
the question is,
Can I answer this, please? That's a very good question, and I can only tell you that there's one established property. It should be Majorana particles should annihilate with itself, and a strong prediction is that whatever, because the annihilation signature depends on the projected density, square density. The CDM model predicts there should be gamma ray excess coming from the center of galaxies, like Milky Way, and so we have actually observational campaign looking for this prediction. So there is strong prediction.
So my question wasn't that.
It cannot be just arbitrarily completely anything because there will be.
Physics is not the science about the angular logic. I mean,
True.
You have to be able to study each piece of your model.
But you are catching two words, which this is exactly angelology. Everybody basically, I think, knows what is a problem with dark matter. Without dark matter, this galaxy formation codes do not converge on results which resemble what we observe. And if it's so weakly interacting, it's very difficult to catch experimentally, and the world around us is full of experiments looking for signature of dark matter. Some of them are carried on the International Space Station, some of them are carried in the deep mine somewhere, and so on and so on. People are working hard.
the question is that if there is a,
So this is science and not embryology.
no, the science will be if I have a model of this dark matter, and I would like to know what are the properties of that, whatever we call dark matter. And then if I know details of that property, maybe I can envisage an experiment.
Yes.
Which will catch it.
Initially-
And not necessarily far away in the universe.
I would be on the same boat.
Because otherwise I know, but it resembles this endless discussion about the properties of ether, which were in the 19th century. There were thousands of models. There were hundreds of papers, well, scaled down by the fact that there were no other scientists working on it.
Yeah, but on
At
the
that
other
time,
hand,
there
we
was-
know that we need something, right? And
Yeah, but the
this is
people
not
in the
a-
19th century were absolutely sure that they need ether to explain the phenomenon.
And phlogiston before
and
that.
It turns out that they were completely, totally
Yes.
wrong.
Could I say something
And
for
the
this?
question was that they have to ask the proper question. And one of the arguments about the ether was that if the ether was existing, that they didn't couple properly to the observations. And the observations were invented by Michelson and Morley
Yes.
in order to check the properties of an ether protected by those models.
So this is why
And
those
therefore it was
observations are
not
now
that
being performed.
everybody was agreeing before that ether couples very weakly to the matter. But there was an experiment invented because the properties of ether were checked.
If I
It
can,
was not the coupling between the ether and the earth which was checked.
if I can offer a concluding
It was
remark to
the
this.
property of an ether which was checked by the Michelson and Morley. And then I'm asking, unless we have to think about what are the
Yes.
properties of this dark matter, and then maybe invent that. I know this is an impolite question.
No, it's not very polite.
I apologize for asking it, but
If I can offer some concluding remark.
The word science is progressing. I think I have enough questions.
Thank you very much. It's a very valid point. I'm on the same boat with you. The problem is no one on this planet knows better because we have definitely facing a lack of the proper theoretical development. No one have come up with the good model. That's also a problem for the model of standard elementary particles. They cannot explain, for example, all the mixing angles and free parameters. They're just phenomenological model. So definitely we are facing huge challenge on both sides. And maybe what we see is actually surfacing the problem that we're lacking the proper fundamental theory, both for dark matter, both for gravity, and both for standard model for elementary particles. Because so far, no theoretician on this planet came up with the proper model with enclosed Lagrangian that would be extension of the standard model of elementary particles. We cannot conduct this really target experiments. I would love to see Lagrangian for dark matter, one prediction. We sit down, we find different experiments like for gravitational waves and try to capture it. Unfortunately, this theory does not exist. It's just purely phenomenological, just like standard model. And that's why it's so vague. It's also not appealing to me, but we don't have anything better. Unless you can come up with something better, I will be the first to give you bravo. So sorry, I mean, I also live with the bitter taste, but this is still reasonable science to try to find observational evidence. Maybe you can learn something about the microphysics by observation of the galaxies, and we could find some insight to the Lagrangian and maybe give hints to our great theoretician or theoretical physicists on this planet. Again, thank you very much for your attention.